but in a nutshell, bases accept and acids donate, right? So bad, that's the little way that one can remember that. Bases are proton acceptors and acids are proton donors, and that's the sort of the Bronsted-Lowry theory on acid-base chemistry. And also embedded within this slide is a rendering of conjugate acid-base pairs. And with this reaction, we have two, right? This is a reaction, or I guess an ionization of acetic acid in water, forming the acetate anion. And the first acid base conjugate pair, of course, is acetic acid, acetate. Now it's going to have a salt associated with it, typically sodium or potassium. But that's the first acid base pair. And then the other one, and I mentioned, water plays an inherent role in acid base chemistry. And so water is also an acid base pair. On the left side of the equation, water is a base and it receives the acid, right? So it's a proton acceptor. And then on the right side of the equation, we have the hydronium ion, which is the acid form in water. Okay, everybody okay with that? Nathaniel?
Yeah, yeah. So basically, the water is either the acid or the base, depending on whether it loses or gains the proton.
That's exactly right.
Okay.
That's
So
exactly right.
when it goes to hydronium, then it was the acid. If it went to the hydroxide, then it was the base, becoming
That's
the.
right.
Okay.
Yeah, yeah. So if it were to if H2O were to lose the proton here, if we had it reacting with a base, then the H2O would become a hydroxide, right? And so you would have it acting as an acid, H2O acting as an acid to give up that proton, and it becomes a base, the hydroxide. So that's a good point, and we'll talk about it again. It's an amphoteric molecule. It has both acid and basic properties. Okay?
Thank you.
All right. Any other questions? All right, let me get back to my... All right, now we're going to get right into some calculations here, and I'm going to try to do this. We're going to try to do this before we time out because we only have 40 minutes. So we're going to try to work this out as best as we can. This example, hydronium ion concentration and the hydroxide ion concentration, what are they in pure water? And I'm sure you've have done a couple of these, but if you will remember, and I'm going to have to catch up here. Let me go back up here and start my annotation. All right, so you'll remember KW is the equilibrium or the ionization constant for water. KW is equal to the concentration of hydronium ion times the concentration of hydroxide ion, right? And that is because if you take H2O plus H2O, you get it's self-ionization, auto-ionization as they call it. I'm sorry, get rid of, let's see here, let me just cross out that is equal to OH minus plus H3O plus. Okay, so that is the reaction. And by the way, is everyone seeing me right on this screen? You seeing what I'm, okay, thank you, appreciate that. So this is the reaction, This is the chemical reaction, and then the Kw is the expression for the equilibrium constant for this reaction. And remember, for in the case of water being the solvent, it is so large, it is essentially constant. It's not going to change concentration appreciably in these reactions. Therefore, we leave it out. So, so therefore, if we want to calculate the concentration of hydronium ion, we would say, let's go back to our equation and put H3O plus concentration is equal to Kw over OH. Okay. And in fact, well, I'm going to do this a little bit of a different way. Give me just a second. I'm going to do this a little differently here. We also know here that that because one hydroxide forms for every hydronium ion. If you just look at that equation, there's no other way around it. You're going to, for every hydroxide, you correspondingly and simultaneously generate a hydronium ion. So therefore, the concentration of OH is equal to the concentration of H3O plus. Okay, so you can therefore say that, I'm going to come over here a little bit, Kw is equal to H3O plus squared, right? And therefore, concentration of H3O plus is equal to the square root of Kw, and that's equal to the square root of 10 to the minus 14, and that's equal to 10 to the minus 7 molar. So that's the concentration of hydronium ion, and also by given this equation here, we know that the hydroxide ion concentration is going to be the same as hydronium ion. Okay.
A quick question with the that equation right there. How did we get the squared? Or
yeah, that thank you for that, Connor. And the reason we get that squared again is when H2O, when two H2O molecules react with each other in an autoionization sense, we get the formation of one hydroxide, and we get the formation of one hydronium ion. So it's inherently a one-to-one relationship, okay? So the hydroxide ion concentration and the hydronium ion concentration are in fact equal, okay? Does that make sense, Connor?
yes.
Okay, good deal.
Yes,
And so
thank you.
yeah, and so you can just plug one into the other as we did, and you can take the square root in that case. Okay, any other questions? All right, now I'm gonna again go through and actually let me just do a clear, because if I don't clear it, it will hang around, believe me. Learned that the hard way. Okay, let me go back to my mouse here and we will go right on. All right, here's another one. All right, okay, so if water solution is acidified, producing a hydronium ion concentration of 10 to the minus fifth, can there simultaneously be a concentration of hydroxide ion in the same solution? So let me hear someone answer that question for me, and I'll get ready to, we'll work it out. Anybody hazard a guess? Think about what we did on that last slide.
Yes.
Yeah, absolutely. You're exactly right. Certainly we can, and let's let's look at that. So I got to go back to my. In fact, let me bring this over here. Oh yeah, that'll be a lot easier. All right, bring my cursor around here. We can calculate this out. Kw is equal to the concentration of hydronium ion times the concentration of hydroxide ion. Okay. All right, and we were given the hydronium ion concentration of 10 to the minus fifth. So let's therefore say 10 to the minus 14th, that's Kw, right? Divided by 10 to the minus fifth, we're just bringing our hydronium ion concentration over 10 to the minus fifth is equal to the concentration of OH, right? And if you were to go to your calculator, which I took a moment to already do because we are a little bit time squeezed, but you will find 10 to the minus 14th divided by 10 to the minus 5 is going to be 10 to the minus 9 is equal to the hydroxide. Okay? Is that okay with folks? Okay. All right, we will go ahead and proceed right on. And move right on to the next slide. All right, we're going to derive the pH and POH given Kw. What equate and I'll show you what where I'm going with this once we solve it. So if Kw is equal to the product of hydronium and hydroxide, then we can take, well, go back. Let me go back up here. All right, got that. Okay, so let's take the minus log of Kw is equal to the minus log. I'm going to shorthand this a little bit, but I think you see what I'm doing as OH, right? And that is also equal to, based on the rules of logs, that's equal to the minus log of H plus, and then plus the minus log of OH. Okay, and that can be therefore reduced to pKw is equal to pH plus POH. All right, so that's a very helpful equation in that you can calculate POH if you know pH, because of course pKw is 14, right? The log of 10 to the minus 14 is 14. Just again, log of 10 to the minus 14 is equal to 14. That's the pKw. Okay. So again, it's just helpful to have that in your back pocket if you need to convert or to calculate the POH or the pH given the other partner there. Okay. And then again, that's
one quick question.
Yes, sir.
So with this equation, will pH always be the log of the hydronium or the H plus, and the POH will always be the concentration of the OH?
Every time. Yeah, absolutely. pH is always going to be the concentration of the hydronium ion in that solution. Same thing for hydroxide. Yes.
Okay.
Any other questions? Thank you guys, appreciate that. All right, I'm gonna clear that and we're gonna go down to our next one. All right, quick set of questions here. True, false. Ka is proportional to the strength of the acid. You guys can give me, you can take a moment and I'm going to try to pull up my, for some reason it's not letting me. Oh, there's my chat box. Let me get someone to say, give me a true or a false on that. You can just send me a quick chat, true or T or F.
It's a guess. True.
You're absolutely right. Okay, and now since let's take the guess part of that out. So if you have H, I'm sorry, let's see, can I get that? Yeah. If you have, let's just say a generic acid, HA plus H2O, that is in equilibrium with, of course, the formation of H3O plus A minus, right? That's the generic equation for an acid-base equilibrium. Y'all agree with that? All right, and so K, therefore, is going to be equal to H3O plus times A minus over HA, right? So Ka, and this of course is Ka, I left my A off, but Ka on this side is proportional to the hydronium ion concentration, isn't it? It's because the hydronium ion concentration is in the top part of that fraction. And that's why, Connor, you're right, that was true, okay? Does everyone see that? So far, so good? Connor, did that help?
Yes, sir.
Okay, wonderful. Good deal. All right. All right, let's moving right along. The first one, Kb is inversely proportional to its conjugate acid ionization constant. Anybody want to hazard a guess on that one? And again, since we let me do this. Let me clear my drawing there. K W is equal to K A times KB. This is another one of those equations that's good to have in your back pocket, right? So just following up on this guy right here, basically what we can do is we can rearrange this, and I unfortunately run out of a little bit of room here, but let's go over here and we can do KW, I'm sorry, K, we can rearrange this and put KB on one side and put KB is equal to KW over KA, K sub A. So does everyone see that? So yes, Kb is inversely proportional to its conjugate acid. I think I wrote it the flip side, but you could put Ka over here if you wanted to, of course, because that relationship, and you could do Kb is inversely proportional to Ka. Okay, so that guy's true, that guy's true. For a hypothetical acid with a Ka of 10, what is the Kb of its conjugate base? Well, again, you could actually use this equation here, couldn't you? And we could, let's just get our eraser, and instead of having Kw, we can now put, we had the Ka of 10, and we know that Kw is 10 to the minus 14. And that's 10 to the 1, I guess, right? So what is the KB of its conjugate base? And I think if you went through and you did that ratio, and you would get 10 to the minus 14th divided by 10, and that's going to be equal to 10 to the minus 15. Okay. Now, this, and please stop me if you need any clarification, but I'll move forward unless I hear from you folks. And I'm also kind of keeping an eye on my chat. So, all right. So, what is the P acetate of a solution of an aqueous acetic acid that has a pH of 4? Well, the acetate, okay, is forming from, let's just call acetate HA plus I'm sorry, it's H2O plus HA is going to H3O plus A minus, right? So the acetate and the hydronium ion, again, I need a plus there, they're going to be exactly equal, right? And so the P acetate, which is, instead of using pH, you can put in the corresponding anion there, and that's what this equation is getting at, is you can, instead of just asking for the pH, you could also ask for the P acetate. And that's what this equation is asking about. It's just a terminology, but you can use the P function for any ion. And so absolutely, they're going to be the same, one and the same, because of the, for every acetate that has formed, it has by definition formed hydronium ion, right? One and one. So one relationship.
So is the
Okay.
P acetate, is that referring to the hydronium or the?
Yeah, again, the pH is referring to the hydronium ion, and the P acetate is referring to the anion here, which is what forms when acetic acid is ionized and goes to acetate. Nathaniel, you need to unmute. Nathaniel, you need to unmute your thing there. Yeah.
Okay, so we're now okay.
I got you.
So you've got the hydronium there, and then you're saying the acetate has a pH of 4.
No, what we're saying here is that we have a solution that has a pH of 4. Okay, and the reason it has a pH of 4 is because we've put acetic acid in that solution, and it has ionized to the extent that it has created a pH of 4. Okay, and therefore, if it's a pH of 4, then the concentration reflects that, and the acetate has got to be the exact same concentration.
Okay.
Yeah, that's really all that's saying. It's just saying that when you form a proton from acetic acid or any acid, you're going to also form an anion, if you think about it. Yeah,
so,
HA going to H plus A minus.
So, for instance, it could say the same thing and say it had a pOH of 6.
Mm-hmm.
And it would still be the same answer, correct?
If it so
or
you
no,
could,
no, it's 14. Yeah, never mind. I was going with 10.
But if you had let's
It'd
just
be
carry that
10.
right, exactly.
The
Now,
pOH of 10 would have a pH of 4.
that's right. Exactly. That's exactly right. And that goes back to pK is equal to pH plus pOH. Yep, that's a very simple. All right, so here we've got H3O plus is equal to 0.1 molar. Now, does everyone agree with that? Concentration of hydronium ion is equal to 0.1 molar. Well, as you're thinking about it, let me just kind of a quick reminder here. HCl is a strong acid, so HCl completely ionizes in solution, okay? So HCl plus H2O is going to go to H3O plus Cl minus. And that is completely driven to the right. Okay? Everybody okay with that? So therefore, 0.1 molar HCl is equal to the concentration of hydronium ion. So the pH of that is equal to minus log of 0.1, right? 0.1 molar, and that's equal to minus log of 10 to the minus 1, and of course that then you can plug that into your calculator, and that equals 1. Okay? Very good. Now, same thing for the hydroxide. OH concentration. This is a strong base, so therefore it completely ionizes. So OH is equal to the concentration of NaOH. Okay. And let me jump up here and just put that for completeness. Okay. And then that equals 0.1 molar. And therefore, in the POH, if we want to take that a step further, equal to the minus log of 0.1 is equal to minus log of, well, 10 to the minus 1. 10 to the minus 1, and that equals 1. POH is equal to 1. And if POH equals 1, then can someone tell me what the pH is equal to?
13.
13. Nathaniel, you've got a question.
Yes. Okay. So in these, since it's dealing with a molar concentration, the 25 milliliters has nothing to do with it, right?
That's exactly right.
Okay.
Now, the next problem, we will need to think about that a little differently. But for this problem, it's you do not need to. It could be 100 milliliters or 10 tons, you know, because all it's doing is asking essentially for the pH or the concentration of that species in that solution.
Okay.
Very good. Very good
Quick
insight.
question. If it times me out, then that's fine. But how did you know that the OH was 0.1 molar this time instead of the H plus?
Gotcha. Okay, so the reason is it gave us that we had 10th molar